Alright, we get to talk about areas and distances. Most of this is going to be areas. We'll do a little distance stuff at the end. But the idea here is I have a graph of a function and I would like to find the shaded area here. That is the area under the graph of f of x, under that curve, between two x values, x equals a and x equals b. So that's the sort of orange shaded area there. And it's a curvy area, right? If it were a triangle or a rectangle or something, I could find its area easily, but it's this weird curvy shape. So what I do is divide it into strips, and the total area I want is the sum of the areas of the strips, so S1 plus S2 plus S3, etc., all the way up to the last strip, Sn. And if I divide it into enough strips, each strip looks kind of almost like a rectangle. So I can imagine replacing each strip with a rectangle of a certain height that's approximately the same as the strip. So that first rectangle is about like S1, and the second rectangle is about like S2, and so on. And I can find the areas of all those rectangles and add them up. The area of a rectangle is width times height. The width is this delta x width, that is how wide each little rectangle is. And the height is the height of the function. And in the picture it's drawn so that the height is whatever the function is at the right-hand edge of the rectangle. So the first rectangle's height you get by going to x1 and seeing how tall the function is at x1, and so on. So it's f of that right-hand x value is the height. And we'll write that f of xi. So the first rectangle has f of x1 for its height, the second rectangle has f of x2, and so on. That means the area is the width times the height, so that's delta x times f of xi. Okay. I could have done this differently. I could have drawn the rectangles so their heights came from the left-hand edge of the rectangle, or instead picked the middle of the rectangle, the midpoint, to give me the height of the rectangle. And this would give me a slightly different approximation for area, but also close to the area. So the idea is if I want that total curvy shaded area, A, I can approximate it by replacing each strip with a rectangle of area delta x f of xi, and then add all of those up, and that gives me approximately the area I want. It's not going to be exact, but it'll be approximately right. And the idea is the more strips I divide it into, the more rectangles I use, that makes the area approximation more accurate. So if I just use two rectangles, like in the left-hand picture here, the area of those two rectangles is not all that close to the area under the curve. If I use 4 rectangles, it gets a little bit better. 8 rectangles, I get even better. 12 rectangles, it's very close, right? So I'm only leaving out or overestimating areas by tiny bits. And you can imagine if I used like 100 rectangles, it'd be very, very close indeed. So more rectangles, more strips, makes your area approximation closer and closer to the actual area under the curve. Let's look at a particular example. I would like to use 4 rectangles with left endpoints, so we'll see what that means, to approximate the area under the graph of x squared, f of x equals x squared, from x equals 1 to x equals 3. So first let me draw a picture. There's f of x equals x squared, it's a parabola. I'm going from x equals 1 to 3, and so the area I would like is that sort of pale green shaded area. Now, I'm not going to get it exactly at this point, I'm just going to get an approximation to it. And the approximation I'm going to get comes from splitting it up into 4 evenly spaced strips, and in each of those strips drawing a rectangle whose height comes from following that left-hand edge of the rectangle up till it hits the function. So the first rectangle, its height comes from following x equals 1 up till it hits the function, and then drawing the rectangle's top over there. Then at x equals 1.5, I go up, and so on. So what I actually am going to be looking for is the sum of the areas of those 4 rectangles, and that will be approximately the area under the curve. My approximation will be a little bit too small because all those rectangles are a little bit smaller than the corresponding strips, but it'll be close. Okay. The width of each rectangle is that total width of the area in question divided by how many rectangles I'm dividing it into. So it's 2 wide, from x equals 1 to x equals 3 is 2 units wide. I'm dividing it into 4 rectangles, so each one is 1/2 unit wide. And that's my delta x from the previous discussion. And then I have a left endpoint for each rectangle. Remember, the problem told me to use left endpoints instead of right. So I've marked the left endpoints of each rectangle. Those happen at x equals 1, 1.5, 2, and 2.5. The heights of the rectangles come from the heights at those left endpoints, so that's f of the left endpoints. F of 1, f of 1.5, f of 2, and f of 2.5. And if I plug those into the function, that's 1 squared, 1.5 squared, 2 squared, and 2.5 squared, written as decimals. Okay, so now I can write down the areas of the rectangles, which are width times height. So that's 1/2 times 1, 1/2 times 2.25, 1/2 times 4, and 1/2 times 6.25. And then I just add those up. That adds up to 6 3/4. So the total areas of the blue rectangles there, the rectangles given by left endpoints, is 6.75. So that's the approximation I have found to the area under the curve, using 4 rectangles with left endpoints giving heights. The notation for that is L4. So the L indicates I was using the left endpoints for heights, and the 4 indicates I used 4 rectangles. So L8 would be the same thing, except I would have divided it into 8 skinnier rectangles. R4 would be this, but I would be using the right endpoints, and if I wanted to use the midpoints of each little rectangle for the height, I would do M4 or M, whatever number. So 6.75 is the approximation I found. L4 equals 6.75. So the area under the curve is probably a little more than that, but I don't know what it is exactly. It's around 6 3/4. Okay. Here's another situation where we can use approximations by dividing things into little pieces. We know if we have a velocity, we can find the distance an object traveled, because the velocity times time equals distance traveled. Rate times time equals distance. But if the velocity is not constant, we can't do that. If the velocity isn't constant, maybe we took measurements of the velocity of our object every 5 seconds. So at time 0, 5, 10, and so on, we measured velocity, and I guess I should have some units. So time is going to be in seconds and velocity in meters per second. So for example, at time 20 seconds, I measured the velocity of my object and it was moving at 6 meters per second. So my question is, over these 40 seconds, where I was making measurements, how far did the object travel? How far did the object travel during the first 40 seconds? Well, I can get an estimate, right? I don't know exactly because I don't have all the information about velocity. But what I'll do is assume that the velocity in each 5-second interval is constant. So the first 5 seconds, it's going at 2 meters per second. Then it abruptly shifts and goes at 4 meters per second for the next 5 seconds. And then 5 meters per second, and then 7 meters per second, and so on. We know velocities don't really look like this, so it's not going to be an exact answer, but it'll be an approximation. So from time 0 to 5 seconds, I can say the velocity is 2 meters per second. That's what it was at 0, so I'll just assume it stays constant. So the distance during those 5 seconds is 5 seconds time times 2 meters per second velocity, so 10 meters. In the next 5-second interval, from 5 to 10, I say if the velocity stayed at 4 meters per second, the distance would be 5 times 4, and so on. I can do this for each interval, and so that the total distance traveled, I approximate by doing time times velocity on each interval. 5 times 2 plus 5 times 4 plus 5 times 5 plus 5 times 7, etc. I stop with the last interval from time 35 to time 40, and because I was using the sort of velocity at the beginning of each interval, that's 5 seconds long times 13 meters per second. I'm not actually going to use the information about what happened at t equals 40. So if you multiply this out and add, you get 275 meters, right? It's a distance. So approximately 275 meters is how far this object traveled. Now what did we just do? Each of those 5s was a time interval, a delta t, and then the number it multiplied by was whatever velocity I had at the left-hand end of the time interval, right? From 5 to 10 seconds, I used the velocity at 5 seconds, which was 4 meters per second. So each of those is a delta t times v of a left-hand end, so this really is an L something, and there were 8 time intervals there. So it's an L8. I used the left-hand endpoints of each time interval, and there were 8 little time intervals I did this on, added it all up, so I found a L8 approximation for distance traveled. Same thing as areas, only now I was thinking about it as distances, velocity times time. We'll do more of this in class, but for now, what I want you to bring to class is, if you have this curve, and you want to approximate it using right-hand endpoints with 3 rectangles, what would those rectangles look like? So draw the rectangles for the R3 approximation of the shaded area. And I will see you in class.